continue the second talk in the morning, given by Professor Wei Tzu-Chieh, and he's going to continue his talk on topological entanglement and minimally entangled states for geometric measure of entanglement. Let's welcome him.
Thank you. So this is going to be a continuation, but I'm going to.
Where the microphone?
Oh, is there a microphone?
Yes, I think on the paper, I left on the table.
Oh,
Button push.
Push the button, or maybe it's already on. Okay. Can you hear me? Okay, so it's going to be a continuation, but I made it so that it goes somehow like a second module. So if you don't, if you were not here, that's still okay. And I may not have enough material to for the 45 minutes, so I may switch to the part 3 before the afternoon session. Okay. So this is what I introduced yesterday, and I sort of illustrate the topology dependent ground state degeneracy. You also heard this in the morning, and also illustrate these in the torical that these degenerate ground states cannot be distinguished locally, and I also illustrate the long-range entanglement by constructing RG transformation that actually flow the torical wave function to a fixed point. And I gloss over this part, but maybe I'll say a little bit more today. So let me just recapitulate the motivation why we want to use entanglement. If we have something that we can just calculate and that tell us there is a topological order, then that's a good thing. But also the downside is that if you just use one number, then you cannot tell the difference of different topological order. It turns out that using entanglement in a slightly different way, that you can actually extract further information. Okay, so this is the outline. So I covered this yesterday, and this is what I'm going to talk about in this lecture. And maybe I will already enter the third part. So as yesterday, just interrupt me anytime if you have questions. Okay, this is from yesterday. So we construct the torical on the torus, and the upshot of that is the torical ground state has fourfold degeneracy, and they can be labeled by eigenstates, or for example, these Z operator, logical Z operator. We could also construct, so the Z, maybe let me review a little bit. So Z operator are constructed on these two curves, and they are product of sigma Z along the one curve, defined as the logical Z operator for qubit 1 and logical Z operator for qubit 2. Recall that the qubit lies on the edges, not on the vertices in this torical model. You can also define the logical X operator that lies on the edges cut across by these two curves. And you can verify that they satisfy the usual commutation relation for two qubits. And since these operators commute with the star and pocket operator, their actions on any of the ground states still remain in the ground state. Okay, so that's a brief review of what we have done. So yesterday, I briefly mentioned the excitation. So you can construct the excitation by applying, for example, a sigma z operator on this qubit, and that will generate the so-called electric truth, a pair of electric charge, and you can move around these charges by applying further operator z, form a string-like pattern. You could also create the excitation magnetic flux or magnetic charge applying using the Pauli X, and you can also move around. And then there's another type of excitation that can be regarded as bound state of electric and magnetic bound state. So including the vacuum, there are 4 different types of excitations. So this is the same as degeneracy equal to 4 on torus, and this was mentioned by Xiaogang earlier. And there are some pictorial understanding of this. For example, the ground state that is constructed by applying all the star operator, and then you make superposition of them, can be regarded as superposition all possible loop configuration. And for this particular ground state, 0, 0. And for the other ground states, that are applied by these logical X operator, you can regard them as sum of configuration with loop that actually wind around in this direction or that direction. So these other ground states have non-trivial winding loop configuration. And in terms of the logical Z operator, the one that I define, the basis of the ground state that I define by such construction, you can show that they are eigenstates of the Z operator. So basically, I label them by 0, 0, 0, 1, 1, 0, 1, 1. It's quite easy to read. If this is 1, then it's a minus sign for this Z1 operator, and the Z2 operator act on the ground state would give a minus sign, depending on the beta. Okay, so that's a complete basis for describing the ground space. And so yesterday, we also go beyond study the torical by applying the string tension in some sense that at each side, I want to give more weight to the 0 state and less weight to the 1 state. So in a pictorial way, it frustrates large loop. And we show that using entanglement, that we actually see a sharp transition. This is the topological contribution from the geometric measurement, geometric entanglement that I defined. And we also compare with other entanglement measure, for example, Rayleigh entropy, and we see that we try very hard to optimize those, and we did not get quite sharp transition using other quantities. So this demonstrates there might be some numerical approximation that you have to make, because these you require 2-layer. In general, for example, the topological entanglement entropy you require 2-layer contraction. So numerically, that's not efficient, especially near the transition. The accuracy may not be very good. Okay, so today I'm going to use the entanglement in a slightly different way to extract further information. So I'm not sure this is the correct terminology, but I'm going to introduce this, and I call this topological charge basis. What I mean is that I want to find a basis of ground states described by Wilson loop in the same direction. So for this basis, they are eigenstate of these operator, Z operator, and also this operator. But if you think of this way, if you were able to measure your spin in this direction, in this region, so the information carried by these logical operators can actually be obtained by your measurement. But the information in this direction cannot be obtained. So it would be desirable to construct certain bases where if you only are allowed to measure your spin in part of a region, still non-controllable, but in one direction of the torus, and then you may be able to extract more information about the ground state. So I can define these eigenstate in terms of Z1 and X2. So X2 are product of sigma Z operator, sigma X operator on these edges. So I just define these. So the first one, so I define the eigenstate of these in terms of these operator. But these four states, it's just a basis change from what I have here. So you can easily verify because we already constructed foreground state. You can just, by direct calculation, the 0 plus minus 1 is actually a superposition of the 0, 0 plus 0, 1. Basically, the second logical qubit is in a superposition. And also the one with 1 plus minus, I did not change the Z1, so this one stayed fixed. And the second logical qubit is in a superposition of 0, 1. So as I remarked yesterday, this really looks like two logical qubits. Okay, so as I mentioned that for these ground state bases, measurement along these directions can extract information. So suppose you were able to measure a product of spin that give you the Z1 eigenvalue, and you could also measure the X2 eigenvalue, so you will be able to know which ground state you are in. So in some sense, this is the so-called minimal entropy state because you have a lot of information along this direction. So this was actually proposed by Zhang et al. That they call these minimal entropy state because they define this in terms of entanglement entropy. Okay, so that I call this, we have definite charges with respect to horizontal loop. And so we expect that if you cut across this and you calculate the entanglement entropy of this part with respect to the other part, then this will be minimal because you have a lot of information about it. So, so these charge bases are argued to have the minimum entropy. So they call this minimum entropy state. So I'll label by theta. And parallel here meaning I cut respect to this cut, or respect to these two Wilson loop parallel to the horizontal axis. So they argue also previously by Dawn et al. They argue that if you compute the entanglement entropy for multi-connected region, actually the value would depend on which ground state you use. So they also have argument from using the so-called strong additivity of entropy. I will not repeat the argument here. And so yesterday I construct the ground state in one particular basis, and I show that the total geometric entanglement can be expressed in terms certain boundary law plus a constant term. In fact, the total geometric entanglement also depends on the choice of ground states. And so the question that we like to ask, can we use such dependence to identify the minimally entangled states? So I now refer to this as minimal entanglement because I'm going to use an entanglement measure. So why are these useful? So we have these charge bases, the four state in this charge basis, and suppose we rotate by 90 degrees. The 90 degrees, so this curve would rotate to this axis, and this C1, CZ1 will rotate to CZ2. So you can see that in terms of the original basis, it's just exchange of the two qubits. So the qubit 1 is exchanged to qubit 2 and vice versa. By doing this, you can see that this charge basis is rotated by this matrix. And this is in fact the S matrix that Xiaogang mentioned in the morning. So this is a modular S matrix and actually describe the mutual statistics of these quasi-particles. So maybe I don't need to say too much on the modular transformation, but briefly this is just a change of basis, or how you glue back your torus. And suppose you identify the coordinate z with this direction omega 1 and this direction omega 2, and the transformation you can consider transformation that change the way you glue back a system, and this transformation, the so-called modular transformation, is described by SL2Z group. These are integer number A, B, C, D, and they form a group. And it was known that this group is generated by two matrices, the S in terms of 90-degree, in terms of square lattice, this simply is a 90-degree rotation because the 1 is rotated to 2 and 2 is rotated to the -1. So in terms of square lattice, this is a 90-degree rotation. And the other one is the other generator is the so-called Dane twist. Basically what it means is the first direction is transformed such that it adds the second direction to the first axis. So in terms of this picture, it means that the first one originally is this red curve is twisted around in the second direction before going back. So this is the Dane twist. So this actually gives the statistics of the particular type of quasi-particle. So in terms of these charge bases, they actually form a representation, modular representation for these modular transformation. So schematically, this is just describe the mutual statistics of different quasi-particle. And then for the Dane twist, this will be diagonal, and this just tell you the statistics of the particular type particle alpha. So it is useful to notice that when you have 120 degree in the system, if your lattice, say a triangular lattice or honeycomb lattice, then 120 degree is a symmetry, then T times S is actually a representation of 120 degree rotation. So I think in the morning Xiaogang used 60 degree, but this is then it will be S times T. When your system has a symmetry, then you can take advantage of that. So what is the relation of the maximally entangled state and modular matrices? So as I said, these form a representation of these modular matrices. And so if we were able to take this basis and then do a 90-degree rotation, as I did in the previous example, and then you can extract the modular S matrix here. And if your system has a 120-degree symmetry, then you could extract T times S, and then altogether you may be able to extract both. So here I only consider one cut, but you could also consider another cut. For example, if you have also the perpendicular cut, then the two set of charge bases, if you calculate the inner product of that gives you also the modular S matrix. But there is some ambiguity of the phase because you may have extra phase multiplied by this basis. It's not exactly 90-degree rotation, but once you get rid of the phase ambiguity, you can obtain the modular S matrix. Okay, so I will just show you some results from finite systems that we have. So, so we did this on torical, but we choose a honeycomb geometry, periodic boundary condition, and so you see that so I have a dashed line that indicating the cut, and I have 20 spin because you count edges. There are 27 edges. So you can parameterize the ground space. So these are my basis using G alpha beta, and I parameterize this. So how do I find the minimal entangled state? I just follow the procedure that first I allow all these variables to vary, and then find the one that is the minimally entangled across the cut. So recall that my geometric entanglement has to be defined with respect to some partition. So once you find the first globally minimal entangled state, then you restrict your Hilbert space to be orthogonal to the one that you found, and then you find in that subspace the minimal entangled state, and you keep doing that until you find the third one, because the fourth one would be determined by the orthogonality from the other three. So from this procedure, we indeed find that these 0, 1, and plus minus, the full ground state with respect to the horizontal cut, indeed all have the same entanglement. In this case, is equal to 6.0. And these four states are the only four states with such entanglement. All the other states have higher entanglement. We verify numerically. So from that, we can also do the rotation. So because we have a description of the wave function, we can rotate it by 90 degrees and calculate the modular matrices. Or else we could also numerically determine the minimal entangled states across the vertical cut, and then calculate their inner product. But you have to get rid of the phase ambiguity. Once you do that, you obtain this. This is exactly what I showed earlier. So we also go beyond the torical, and we also check the double Samuel model. But maybe before that, I just want to mention that. So there's a vacuum indicating by this, and it has no any statistic with other particle. But you see that there's a minus sign here indicating that the E and, for example, E and M, they have a -1 statistics. So they are called relative Samuel, although they are boson themselves. And we also do this for the double Samuel on the same lattice here. And we find interesting that they all have the same entanglement as the one with torical. So if you want to use entanglement to distinguish the two models, you cannot do that because they all have the same entanglement. But if you carry out this procedure and calculate the modular matrix, for example, the S matrix, you do see that they are different. Even under permutation, they are intrinsically different. The diagonal has a minus sign here. So they are indeed a different topological phase, in different topological phases. So with the competence we obtained from these Abelian model, we actually try to do this for double Fibonacci model. And the wave function are described by these branching rule and these consistent relation. So the upshot is that we were able to write down the four degenerate ground state wave function and carry out the procedure. So the four degenerate ground state, when we do numerical search, what we obtain is that they do not have the same entanglement, amount of entanglement, but they somehow arrange in in a pattern that this is the lowest entanglement, and that the upper two have the same number of entanglement, and the higher one is also different. So this is actually reflecting the ground space structure of the double Fibonacci model. It can be actually decomposed into vacuum and two Fibonacci anion and the bound state of it. So because of the symmetry, and we actually try to calculate the rotation of 120 degrees and calculate this matrix T times S. And this is our numerical value. And we compare to the exact value, it seems to agree very well with 1%. Any questions so far? So actually this is probably the end of the part 2, quite short part. So but maybe I summarize what I have talked about from yesterday until now. So I introduced you the so-called geometric entanglement, and I use that to calculate ground state in the torical and also quantum double model. And we found that the entanglement that we obtained seemed to scale with the number of blocks and also the linear size of the block. In addition, there's an additive constant. And this additive constant all agree in the model we examined with the topological entanglement entropy. So we think that this may be an alternative way to extract these topological entanglement entropy and can be used to detect topological order, the existence of it. And we use that ansatz, and then we consider the torical under string tension deformation. Because once you apply the string tension, the torical wave function, the deformed wave function is no longer a fixed point, and as you deform more and more, actually the correlation length actually increases. And we found that even though we partition our system into different ring geometry, even one direction is really small, much smaller than the correlation length, we were able to identify the transition. Somewhat surprising, because for the topological entanglement entropy, if you do the partition, you need to make sure that the region that you divide need to be large enough compared to the correlation length. And just the last 30 minutes, I described you that the entanglement can be used in a way that to find the so-called the minimal entangled states, and the rotation behavior of these states actually encode the quasi-particle statistics, and they are signatures of topological phases, and therefore can be used to give further characterization of the different topological phases. So I guess that's the end of.
My question is, in the first lecture, you defined entanglement using this overlap with some product states.
Yeah.
Can you use that kind of entanglement to determine the minimal entangled states?
So that's exactly what we did.
Oh, I
here.
see.
Yeah.
So
we use the same.
So both Euro entanglement and this overlap entanglement, they both works.
Yeah. So using using the entanglement entropy, and also using this, it also works. So you have to, but the requirement is you need to know the ground state. You need to have a description of all the ground space, and you need to search, do a blind search or systematic search to find a minimal entangled state. And you do this systematically.
I see, but this entanglement can be computed using the Euro entanglement entropy or using your overlap.
Yeah.
Both